Welcome to our next explainer on nuclear chemistry. Today, we're diving into one of its most amazing concepts, this secret clock that's ticking away inside every single radioactive atom.
I mean, how is that even possible? It sounds like two totally different things, almost like magic. But the answer isn't magic at all. It actually lies in a fundamental and incredibly predictable process in nature.
So here's our game plan. We'll start by understanding the core concept, then we'll get the tool we need to decode it. After that, it's your turn to test your skills, and finally, we'll see how all this stuff actually changes the world around us.
Okay, first things first. What exactly is this clock we're talking about? Well, it's a concept called half-life. And believe me, it is the key to everything else we're going to cover.
So here's the crucial point. It's not about predicting when one single specific atom will decay. That part is totally random and unpredictable. Instead, it's about the very predictable amount of time it takes for half of a big group of them to change.
And this is a perfect way to see it in action. Let's take cesium-137. If you start with exactly 1 gram, you know with almost perfect certainty that in 30 years, you'll have half a gram left. Wait another 30 years, you'll have half of that, which is 1/4 of a gram, and so on. It's like clockwork.
You can see why this is so huge for scientists, right? This incredibly steady, predictable decay is like a reliable cosmic drumbeat that we can use to measure time on an absolutely vast scale. But to actually use it, we have to translate this rhythm into a usable formula.
So to read this atomic clock, you kind of need a decoder ring. And in science, that decoder ring is usually an equation. But don't worry, this one is way more straightforward than it looks.
And here it is. Now, I know it might look a little intimidating at first glance, but all this formula is really doing is this. It starts with the amount you began with, and then it multiplies it by 1/2 for every single half-life that's passed. That's it.
Let's actually break down that code. N0 is your starting point, your initial amount. Nt is what you're trying to find, the amount left over. The real magic happens in that little exponent. You take the total time that's passed, T, and you divide it by the substance's specific half-life, T1/2. That simple fraction just tells you how many times you need to cut your starting amount in half.
All right, enough theory, right? Let's get our hands dirty and actually put this into practice. I'm about to show you 5 challenges, all based on real-world isotopes. Feel free to pause after each one and try to solve it yourself. We'll go over all the answers in the next section. Okay, first up, iodine-125. This is used in medicine. So if we let 3 of its half-lives go by, what's going to happen to our original sample? Just think about it simply. What does it mean to cut something in half 3 times in a row?
Now for a classic you've probably heard of, carbon-14 dating. If you find an ancient piece of wood and it only has 1/4 of its original carbon-14 left, well, how many half-lives must have passed? That's the key to figuring out its age.
For this one, we're going to flip the script a little. We know the start and end amounts for this sample of tritium. Your job is to figure out how many half-lives it took to get from start to finish, and then use that to calculate the total time.
Next up, samarium-153, which is used to treat cancer. Now, after 8 days, we don't really care about the exact amount. We just want to know the fraction that's left. So, how many 2-day half-lives can you fit into 8 days?
And for our last one, this is the real challenge. We're going to solve for the unknown. We've got a super old rock that has only 1/16 of its beryllium-10 left. If we know that took millions of years to happen, can you work backward to figure out the length of a single half-life?
All right, time's up, pencils down. Let's walk through these solutions together and see how you did.
For our first problem with the iodine-125, you just have to apply the rule 3 times. You start with 20 milligrams. After 1 half-life, you're at 10. After a second, you're at 5. And after the third, you land on our final answer, 2.5 milligrams.
For the carbon-14 artifact, having only 1/4 left means 2 half-lives must have gone by, right? First half of it decayed, and then half of what was left decayed. So you just multiply 2 by carbon-14's super long half-life, and you find out the artifact is almost 11,500 years old. To get from 100 grams of tritium all the way down to 12.5, you can just map out the journey. 100 becomes 50, that's 1 half-life. 50 becomes 25, that's 2. And 25 becomes 12.5, that's 3 half-lives. So we multiply 3 by its 12.3-year half-life to get a grand total of 36.9 years.
The samarium-153 problem was just about the fraction. Its half-life is 2 days, and we're looking at what happens after 8 days,
Well, 8 divided by 2 is 4. So exactly 4 half-lives have passed. That means we multiply 1/2 by itself 4 times, which gives us a final remaining fraction of 1/16.
And for our big final challenge, we had to work backward. A 1/16 remainder tells us that 4 half-lives must have passed. So if that entire process took 4.14 million years, we just divide that total time by 4 to find the length of one single half-life. And it comes out to just over 1 million years.
So we did all that math, but why? What's the point? Why does any of this actually matter in the real world? Well, now that you can officially read the atom's clock, let's look at the incredible things it allows us to do.
And this is where it all comes together. It turns out the length of an isotope's half-life basically determines its job. Isotopes with short half-lives are perfect for medicine. They can go in, deliver a targeted dose of radiation, and then safely fade away pretty quickly. Meanwhile, isotopes with incredibly long half-lives are perfect for geology and archaeology, acting like these ancient clocks that let us read the history of our planet.
And all this leaves us with one final, kind of mind-bending thought to chew on. If you only ever lose half of what's remaining, does the original substance ever truly, completely disappear? We've learned how to read the atom's clock, and it looks like it's measuring a countdown to infinity. Thanks for joining me on this one.